Okay. So let me start sharing my screen.
Mhm.
All right. So last time, maybe just to remind everybody, if you were here or if you weren't here, just to catch you up a little bit, what we did was we just defined open book decompositions and fractional Dane twist coefficients, and started talking about Higard-Floer homology and the invariant, the contact class in Higard-Floer homology associated to an open book decomposition. And we left off by just talking about some key properties of this contact class. To remind you what it looked like, the idea was if you started with an open book decomposition, you kind of drew some arcs on it, and then you turned it upside down and kind of stuck the two ends together, and you got these natural intersection points here, which give you a generator in Higard-Floer homology, and that generator ends up being an invariant of the contact structure associated to the open book decomposition. So the important properties that we just kind of wrapped up with last time were that it doesn't completely detect over-twistedness or tightness, but it will tell you that if it is over-twisted, then your contact invariant is 0. It's possible that it could be 0 and your contact structure is still tight, but if you assume further that it's not just tight but fillable, then in fact you get that the contact structure is non-zero. And the other key property is that if you take some curve in your open book, then if you add some Dane twists along it, then the contact structure or the contact invariant is natural under the cobordism map associated to that adding of Dane twists. So you can view that as like a surgery along a curve in your manifold that gives you a map in Higard-Floer homology, and the contact invariant is natural under that map. And then finally, just one more property, which is useful for us, is that if you have some open book with connected binding and your twist coefficient along that single binding component is big enough, then you not only get that the contact invariant is non-zero, but in fact, some reduced version of the contact invariant, which I'll define in a second, is non-zero. So just as an example to kind of wrap our heads around what the contact invariant is doing, if we just look at kind of the simplest possible open book decomposition, which should be like the disk open book decomposition for S3, which is also the same thing as the contact invariant for the annulus with the Dane twist, because those define the same contact structure, then this guy here is non-zero. And you can see that just because you have a kind of dumb Higard decomposition of S3, which is just like a sphere essentially, right? With no intersection points. It's one way that you could see that. Or maybe if it's easier, you could also see it by, say, stabilizing that same picture so that you get a torus. And now you can view the contact invariant as being right here. And there's no disks, so of course it's non-zero. And that actually ends up being the generator for the Higard-Floer homology of S3 in general. Okay. But on the other hand, if you look at a negative Dane twist, so this is like, say, if you're thinking about fibered knots, this is like the negative Hoflink as opposed to the positive one, then this contact invariant ends up being 0. And the reason is simply because if you look here, this is an open book decomposition for the negative Dane twist. Here's your contact invariant. It's that intersection point right there. And you have kind of a obvious disk that kills it. So maybe just some more examples. Here, if you look at the annulus with the identity monodromy, this is something, this is the open book for the standard contact structure on S1 cross S2. And this guy's also non-zero. And you can see that, again, by just looking at a simple Higard diagram, but maybe to use some of the other properties, this is because this is also fillable. You could also use that for this one too. You know that the standard contact structure on S3 is fillable just by the standard 4-ball. And similarly, this guy's non-zero as well. And say if you wanted to use one of the other properties just to get a feel for it, what you could do is you could think about adding a bunch of negative Dane twists along the same core curve, and you'd get down to the identity, which has non-zero contact invariant as well. So the naturality tells you that that one has to be non-zero too. Okay. So something that's going to be really important for us is understanding the structure of Heegard floor groups. So just really briefly, there's a bunch of different groups, but the ones that we're going to be interested in, as I mentioned before, are, is this one, this HF plus group, but there's also a minus group and an infinity group. And I'm not really going to talk too much about these, but the point is that they're different groups that just depend on how you count your U action, which comes from your base point, Z. And the main thing that we need is that they fit into an exact triangle of the form HF minus goes to HF infinity goes to HF plus, which goes back to HF minus. And the idea is that these maps in this exact triangle, this is some type of inclusion map, and this is some type of projection map, and this is some type of connecting homomorphism. And now an important group for us that's going to be important for stating our theorem, which we'll do in a second, is that the reduced Floer homology with the plus version is defined to be, okay, in this exact triangle, this HF plus group you can think of as the as HF infinity mod out by HF minus. And so this should be the co-kernel of pi, which should also be the, or sorry, sorry, other way around. Kernel of pi, which is the co-kernel of I, which is the other guy here. So kernel of pi, which is the co-kernel of this inclusion map. And those are naturally isomorphic by this connecting homomorphism. So one way that you can think about this as this HF minus is kind of counting the U action in a different way. And so this HF plus reduced group, you can think of it as the limit of the co-kernels of U. So if you take a limit as n goes to infinity, and then you look at the co-kernel of different powers of U, then the idea is somehow that in HF infinity, everything's in the action of U. And if you look at the kernel of this projection map, then you'll get out the co-kernel of U somehow. Okay. And now finally, we can just simply define for any element X in HF plus, you can just define an image X reduce in HF plus reduce. So why not just do it for the contact class? So the reduced contact class is just the image of the contact class in the plus version, just inside of the reduced version. Okay, so now we have all the tools that we need to state our theorem. So remember what our goal was. It was to get some type of bound on the fractional Dane twist coefficient after we cap off an open book. So we have some fractional Dane twist coefficient before, we have some fractional Dane twist coefficient afterwards, and we want to understand how it changes. And here's our main theorem, is that if you have some open book for a rational, or if you have some open book which caps off to a rational homology sphere, so this guy here is like your ambient manifold for your capped off open book. So if that's a rational homology sphere, and either one of these two conditions hold, so the first one is simply that the dimension is a vector space over F of HF plus reduce of Y with coefficients in F minus 1. So if your fraction Dane twist coefficient is sufficiently low, or sorry, this should be negative. a negative there. So if your fractional natives coefficient is super low, or if it's just slightly less low, so this is going to be the same thing here, and you just have some other fractional natives coefficient along some other boundary component that's less than 0 for any other boundary component, then you can guarantee that your reduced contact invariant ends up being 0 once you cap off. So this is telling you that if you have a really, really, really low fractional natives coefficient along the boundary component that you're capping off, then if you cap it off, you get some contact invariant for your capped off open book, which cannot survive in the reduced Floer homology. So it's got to be in the image of u to the j for all j. And how does this actually answer our question? It doesn't necessarily seem obvious, but the point is just we're going to use the other property of fractional natives coefficients and open book decompositions with connected binding to say essentially just an inversion of the theorem above in the case that we have exactly two binding components. So this time we're just going to replace all these negatives with positives. So that guy becomes a dimension of the reduced Floer homology plus 1, and this guy's just going to be dimension of the reduced Floer homology without that plus 1. And you just have that. So in this case, you only have two binding components. One of them, you have the fractional natives coefficient is huge, and then the other one, you just have that it's greater than 0. Then finally, what you can conclude is that after you cap off, your fractional natives coefficient has to be greater than -1. And this follows from essentially this last property that we wrote down about the contact invariant. The point is that if you start with an open book decomposition with two binding components and you cap one of them off, then you get an open book with connected binding. And if your contact invariant were non-zero in reduced Floer homology, then if your fractional natives coefficient were less than -1, then taking the inverse would give you something with fractional natives coefficient greater than 1, which would tell you that you're non-zero in your reduced Floer homology. So that's how that follows from our theorem above. Okay, so just as an example, because there's this is kind of a complicated statement, but how can you actually use it? Well, this example we saw last time, it was originally due to Baldwin and Etmeyer. And the point is just that this example shows that your fractional natives coefficient can change by essentially however much you want. So this guy here is some open book decomposition with pseudo-Anosov monodromy. It's got a single boundary prong on each boundary component. And you're just going to do some Dane twists along each boundary component, and then also a Dane twist along this guy, which forms kind of a pair of pants with the two boundary components. And when you cap off this guy, your first boundary component, then you end up with a fractional Dane twist coefficient that can be arbitrarily low. But the point is just that this theorem tells you that if it's low enough, in particular, if it's less than -1, then you have to get out some information about your reduced Floer homology of the ambient manifold that you started with. In particular, you get out that it has to be greater than n1. So this is telling you something about the reduced Floer homology of these open book decompositions, given that you cap off and get something really low for your fractional natives coefficient. So maybe as another example, if you take a fibered knot, say an S3, just for a simple example, and we're just going to specify that the determinant of our fibered knot is non-zero. And let's say that our fractional natives coefficient, fibered knot specifies an open book decomposition, and I mean the fractional natives coefficient along the boundary component. So let's just specify that that's less than 0. Well, then what you could do is you could take the cyclic branched cover over K, connect the positive Hopf link. And if you're interested in, say, like the L space conjecture or something similar than that, then it turns out that this cyclic branch cover is not an L space for some large enough n. And what does an L space mean in our context? Since I haven't defined it yet, it just means something where the reduced Floer homology is non-zero. So here's an example of such a knot K. Just take the left-handed trefoil, for example. And then this picture is K connects a positive Hopf link. And if you take, say, cyclic branch covers along this guy, then you'll see that one of them is not an L space. In fact, I think for this one, it ends up being like the second or something. So how does this proof go? How do you show this? Well, let's just, so if you connect some with if you take a fibered link and you connect some with a Hopf link, then you get another natural fibered link. So it has some open book decomposition, which we'll call SV. And then after that, you can just note that K has open book decomposition given by capping off that Hopf link. So if you kind of like fill in this guy with a disk, then you end up getting your original open book decomposition is the idea. And now by assumption, we assumed that the fractional dangerous coefficient along K was less than 0. So, and we can also note that the fractional dangerous coefficient along K connects some the Hopf link is greater than 0. And this is just because we're stabilizing. So your open book SV is just like a stabilization, some other open book. And so you should have a Dane twist along that boundary component, so your fractional dangerous coefficient should be greater than 0. And now, from last time, we talked about this property of fractional Dane twist coefficients, where if you take any boundary component and you take your monodromy to, say, some power, then the fractional Dane twist coefficient is just multiplied. So if we take some n that's really, really big, well, then we have that this fractional Dane twist coefficient along SV should be greater than whatever we want, but in particular, it should be greater than, like, say 2. And fractional Dane twist coefficient, or sorry, greater than 1. It's enough for us. And fractional Dane twist coefficient of your capped off open book, this was the one for K, should be less than -1. So if you just look at some large enough power of the monodromy, then you get that this is true for your fractional Dane twist coefficient. And maybe note also that S phi to the n is an open book for this cyclic branched cover that we're interested in. And finally, the only last thing that you need to note is that because the determinant of K is non-zero, then this cyclic branch cover over K is a rational homology sphere for some large enough n. So you can apply my theorem to that, and then you get out that you have to have some bound on the Floer homology, or on the reduced Floer homology, and so it can't be an L space, essentially. That's how that goes.
So, Braeden, how do you get S naught back from S after capping off?
How do you get S naught from S after capping off? Oh, yeah. So, yeah. So you want to see a picture for that. So the point is, like, for example, this this knot here, the left-handed trefoil, has an open book like this guy, where you do negative Dane twists, say maybe I'll do in like red or something, along each of these curves. And when you connect some with the Hopf link, what you're doing is you have an open book decomposition that looks like this, where you still do -1 Dane twists along both of these curves. But now you're going to be doing, say this is your little Hopf link component here. You're going to be doing a +1 Dane twist along this curve.
Yeah.
And this is supposed to be, like your K in there. Great. Okay, cool. And so, without spending too much time on like making this statement precise, the point is of this next corollary is that you can do something really similar for fibered knots in more general wise. You just say stabilize it or something like that. Or if you just take something with a fractional natives coefficient greater than 0, then you get something that's not an L space in the cyclic branch cover. Okay. So now maybe as a note, we've really only bounded the fractional natives coefficient for open books with connected, or sorry, with two component binding. And that was because we really relied on that last result, that giving you that if your fractional natives coefficient is greater than 1 for something with connected binding, then you're in the reduced Floer, or you're non-zero in the reduced Floer homology. And so really the only thing that told us about a bound on the fractional natives coefficient was our first corollary. It wasn't our original theorem. So the question is, can we get at something from our original theorem that tells us about bounding fractional natives coefficients after capping off for open books with more than two binding components? Can we do it? Can we do it for more general things? But it turns out this is much, much harder. So the reason why is this example here. So if you just start with, say, this guy, which is a fibered link, H plus connect some H minus, so just a positive and negative Hopf link. So what does that look like? That looks like this guy here, where we've kind of highlighted this green component. And it has the open book decomposition, which is just a pair of pants with, say, a +1 Dane twist along L1 and a -1 Dane twist along L3. And then our L2 boundary components just kind of sitting there. So note that in this open book decomposition, L2 is a 0-framed unknot. And so we can add arbitrarily many Dane twists along it and still get an open book for S3. So we can add arbitrary, say, negative Dane twists. Dane twists. Along L2 because it's 0-framed without changing the ambient manifold. So in particular, if we look at this guy here and we add, say, -n Dane twists for n as big as we want, then that's also an open book for S3. Now, if we just cap off L1, then we get an open book which is an annulus with Dane twist -n-1 along it, because you cap off this guy here, which kills this positive Dane twist. And you're just left off with the annulus with the -n and the -1 from before. And note that this fractional natives coefficient is arbitrarily low, and this is also an open book decomposition for a lens space. It should be like L -n-1, comma -n minus whatever. Which is, of course, a rational homology sphere. Okay. So yeah, the problem is really just that, like I said, our result relies on this theorem that I mentioned before of Honda, Kazez, and Modic and Conway, which is that for if you have an open book with connected binding, and your fractional natives coefficient is greater than 1, then your reduced invariant is non-zero. And so our theorem just doesn't really tell us much about fractional natives coefficients of capped off open books with, disconnected binding. So the question is, can we relate the fractional natives coefficient to the reduced Floer, or to the reduced contact invariant, or some type of analog of it for the boundary disconnected? That's a question that I'd definitely be interested in if somebody has any type of ideas for doing that. So it's a good open question. And I think it would also help with a lot of other things that people are interested too in this area. Okay. So that's kind of some of the examples of things you can do with it, and maybe some further directions you can go with it. But now, how do you actually prove this main result that I stated before? Well, you can kind of prove any type of result in this area that's similar to this one in these kind of three general steps. So the first step is that you need an exact triangle in Higard-Floer homology. This is already given in a couple different places depending on what situation you're in. And for us, Matt Hedden and Tom Mark have already made an exact triangle that we're just using. And the second step is that you need an element mapping to the contact invariant of your open book where you add some Dane twists to it along, say, your first boundary component. So you need some element mapping to that in the exact triangle. And then step 3 is just that you need to show that this element is not in the image of anything from the previous thing mapping into it. And if you can do that, well, then what do you get out? You get out that the contact invariant after you add some Dane twists is non-zero. And so if the contact invariant is non-zero, then that tells you that the contact structure associated to that contact or that open book decomposition is tight. And that tells you that the fractional Dane twist coefficient along, say, for example, your first boundary component, the one where you're adding the Dane twists, is greater than 0. And now, by just additivity of fractional Dane twist coefficient under Dane twists, that tells you something about the fractional Dane twist coefficient of the open book you started with. Okay. So the idea is you start with some exact triangle, you find some element that isn't in the image, and it also maps to the contact class that you're interested in. And then after adding some Dane twists, you get out that that contact structure has to be tight, and so you get some bounds on the fractional Dane twist coefficient that way. So for us, let's start to fill in these steps. So as I mentioned before, the surgery exact triangle is already the one that we're going to use was already written down by Matt Hedden and Tom Mark. And then the element that we're going to use that maps to the contact invariant that we're interested in is actually some contact invariant with twisted coefficients. So I'll talk about that in a second. So it's going to be the contact invariant of your capped off open book with twisted coefficients. And that lives in HF plus of your ambient manifold of your capped off open book. And instead of F coefficients, we're going to use FCN coefficients, where CN is cyclic group. So it's some group ring of some cyclic group over F. And so since this is something slightly different, we need to fill in the details to show that this actually does map to the contact invariant that we want, which is just going to be the same one as before, where you add some Dane twists along your first boundary component. And then that will be the element we're interested in. And then finally, we need to show that that element, that this twisted contact class, is not in the image in the exact triangle. And where is it going to be in the image from? Or our exact triangle is going to be coming from just our original ambient manifold with F coefficients that we started with. And so if we want to show that that's not in the image, well, we're going to need a rank argument. So in particular, for both this guy and this guy, the following theorem is important. So what's the theorem? It's that if you look at this contact class of your capped off open book and some twisted coefficient system, so we need to be careful because it's no longer an element anymore, as I'll explain in a little bit. it's now some subspace of some vector space, and it's generated over F, which this is the theorem that I'll write down. It's generated over F by, in some sense, the elements that you would expect. So just a zeta there. Etc. So it's generated by these x tensor zeta powers in your twisted coefficient system, where x is just the generator for your contact class before, just your regular contact class on twisted, and zeta is the generator for Cn. So this is essentially, you can read this result as telling you that in the twisted coefficient system, nothing really changes about your contact class, that it's just generated by just your regular contact class tensored with the powers of Cn. And finally, the interesting part about this is not just that, but also that if your ambient manifold for your capped off open book is a rational homology sphere, then all of these generators are linearly independent or zero. So that tells you that your rank over F of your twisted contact class is either rank n or just zero. It's just the zero submodule. Okay, so I need to tell you a little bit about where these FCN coefficients come from and how to think about them. So to do that, what you're going to do is, the simple way you can think about it maybe is that you choose some base point on a beta curve. So we're just going to choose some base point P on your beta curve. And then all you need to do is just count how many times any disk that you're counting in your differential crosses P. So for example, in this picture here, you have some disk from X to Y and it crosses P once. So what would you do in your differential? Well, you pick up a power of zeta to the 1 because it crossed P once. So your differential for X would be something like a Y tensor zeta to the 1 because you crossed P once and then plus whatever stuff else you would have from other disks. Okay, so as an example, for our purposes, this twisted coefficient system, we need to specify some base point somewhere. So what are we going to do? Well, here's a Hagar diagram for your uncapped off open book, just for an SV. And now when you cap off, you have a natural Hagar diagram associated to that, where you say take this beta curve all the way to the left here, and you replace it with just the binding component that you're capping off itself. And the point is just that, well, in your capped off open book, your binding component should bound a disk, and so you're making it bound a disk in the Hagar diagram. And now your contact class associated to your capped off open book is this x1, x2, x3, where you're just again replacing your x1 by the natural intersection point all the way to the left. And so the last thing we need to do is just specify where our base point is. And what we'll do is we'll just take a base point on that curve that we added in to cap off our open book. So this is going to define the twisted coefficient system that we're using. And the theorem that I wrote down above tells you that your twisted contact class is simply generated by this X tensor zeta ... X tensor zeta to the n, where X is just equal to this x1, x2, x3 tuple of intersection points. Okay. So the next thing that we need to do is understand how to use this twisted contact class. And in particular, what we'll be doing is we'll be understanding this twisted contact class and how it is carried through the capping off procedure. And in particular, from the capping off procedure, you get some map in Heegard-Floer homology. And it fits into a broader framework of maps in Heegard-Floer homology that come from surgery along some knot. So let's just briefly describe how this works. So how do you do it? Well, if you start with some knot in, say, your ambient manifold, say y1, or, yeah, I'll just call it y maybe. And then you also start with a framing lambda of that knot. Well, you want to find some Heegard diagram where you can kind of see k on it. Or in particular, as you can see here, we kind of replaced our sum curve with a copy of our k. But which curve was it? Well, it was a curve that crossed it exactly once. And so that is exactly a meridian. So you want to see this meridian mu as, say, a beta curve in your Heegard diagram. And now to do surgery, what should you do? Well, you should just replace your meridian with your framing that you want to specify. So if you just replace mu, one of your beta curves, with a new beta curve, which is literally your framing lambda, then that yields just like lambda surgery along k. So that should be a new Heegard diagram for your surgery. So now to make your map in Heegard-Floer homology, what should you do? Well, you make what's called, instead of a Heegard diagram, this is called a Heegard triple. And what is it? It's the same thing as a Heegard diagram, except you have an extra series of curves drawn on it. So you have your alpha and your beta curves, but you also now have a gamma curve drawn on it. So we need to define what these gamma curves are. Well, you're just going to set gamma 1 equal to the curve that you replaced mu with, so just your framing lambda. And then your gamma I is just going to be your original beta curves for I greater than 1. And then finally, to make your map, all you do is, instead of counting disks, you just simply count triangles. You need to count them in a special way, which I'm going to completely gloss over. But what you're doing essentially is counting triangles. So here's an example, which will make it much clearer to see, I think. So in this example, we're just capping off annulus with a Dane twist. So that's like the open book for the Hoff link on S3. And it caps off, of course, to just the disk with the identity, which is like the unknot in S3. So in this example, if we're capping off, we need to draw a Heegard triple. And so what does that look like? Well, we only have one curve for each, so there's our gamma 1. Our beta 1 was the blue curve that we started with. And our alpha 1 is, again, the alpha curve that we started with. So now in our map, what are we doing? Let's see where the contact class is and of each of the original open book and the capped off open book and see where things go. So if we say call this guy, actually, we'll call this one y here. And this one over here will be x. And now the contact class of the original open book is our y. The contact class of our capped off open book is our x. And to see where the contact class of the capped off open book goes under this map, well, we need to count triangles. So what does that mean to count triangles? Well, for example, you have one kind of natural triangle right here, which runs kind of from this x intersection point and this other intersection point here to y. So that's one triangle. But in this map, you actually also have another one hidden somewhere. So where's this hidden triangle? Well, you kind of start going around this guy around the back, And then you kind of come out the front here and follow it along as well. So that's a second triangle. And you can check that there's no other triangles here. And so under the map associated to capping off in Higard-Flare homology, your capped off contact class actually goes to twice your uncapped off contact class because there's two triangles going to it. And just as maybe an aside, to help with these twisted coefficients, if we say put a twisting base point where we're used to putting it just on the capped off curve, on our gamma 1 curve, then you just simply count one of the zetas in one of the triangles in your image. Okay. So now, just to kind of get perspective on how the proof of our theorem is going to go, we're going to kind of practice by proving a similar theorem. So to do that, we need a different perspective on the contact class. So this is all going to be for genus greater than 2, but for genus greater than, or for genus less than 2, you know, it works similarly, but you just need to be a little bit more careful. But the point is that you can define the contact class as the image of some element in a surface bundle where you think about capping off a single binding component. So for a G greater than 2, you have that HF plus of Y0, where you need to be careful about some spin C structure, which I'm just going to completely gloss over. For G greater than 2, HF plus of, this guy here with a minus sign, is isomorphic to just a single copy of F. And so this is, you know, it's one dimensional, is what that's saying. Maybe this should be that guy there. And so it's generated by some, say, like C0. And this Y naught, what is it? Well, this is just your manifold that you get from capping off a connected binding. So it's some surface bundle over S1. So then it turns out that your contact class of your open book is simply the image of this generator of your one-dimensional homology in the right spin C structure, etc., when your binding is connected. And so for your binding disconnected, what do you do? Well, you just simply stabilize to or from an open book with connected binding. And then you can kind of cap off that connected binding to get some surface bundle. And you can see the contact class is the image of that guy. And now for FCN coefficients, it's similar. You just have that the same manifold with the same spin C structure, which I haven't even mentioned how those work. With Higard-Flare homology, this guy should just be isomorphic to a single copy of FCN, and that was due to head and mark as well. So now for your genus less than 2, like I said, it's similar, but you just need to be a little bit more careful about coefficients and stuff like that. So the last tool that we're going to need is a surgery exact triangle. So we have this surgery exact triangle, the original one kind of written down by Oshvath and Szabo, which is just simply tells you that if you look at, say, your ambient manifold, and then your ambient manifold with some different framing, say like a mu plus a lambda, and a lambda, then you get an exact triangle just along those surgeries. So don't worry too much about those framings. For us, what does that mean? That just simply means that if you have some open book, in the case where, say, for example, your binding is connected, then you can simply choose y mu plus lambda to be equal to, say, 0 surgery along that binding component, and y lambda to be equal to, say, -1 surgery along that binding component. And so there's a simpler case of our theorem that follows essentially just from the surgery exact triangle. So we'll just go through that proof to kind of give you a sense of how our proof would go once we have all the pieces in place. So the theorem tells you that if you have some open book decomposition with connected binding for an L space, which is one where the reduced Floer homology is 0, then the twist coefficient of that connected binding has to be less than 1. And here's how the proof goes. It goes essentially according to the steps that we looked at before. So you look at a piece of the exact triangle, and notice that this guy here is where this C0, which is the generator of your one-dimensional Floer homology, is. And your contact class, C of SV, is in there. And this guy here contains the contact class of C of S, where you add a single Dane twist along the binding component. And now we know that this contact class where we add a single Dane twist along our connected binding is the image of some element. Sorry, this should be C0. And I didn't say this before, but it turns out that the U action is trivial. And that's kind of the key property in this proof, is that the U action is trivial on C0. So then it turns out that this C0 cannot be in the image of anything from HF plus of minus y. And that's just because it's an L space. So everything's in the image of U in an L space. And since your U action is trivial, and these maps are all equivariant with respect to U, it can't possibly be in the image of something. So that means that the contact class where you add a single Dane twist is non-zero. That tells you, again, that your contact structure associated to that adding a single Dane twist is tight. And so the fractional Dane twist coefficient is greater than 0. And then that tells you that this fractional Dane twist coefficient is greater than -1. And finally, if you just turn everything around by using the inverse monodromy, etc., then you just get that it also has to be less than 1 as well. Okay, so for us, we need to do something more complicated, because we don't just want to add a single Dane twist, we're going to add lots of Dane twists. So for us, we don't want a surgery exact triangle for just a single Dane twist. And connected binding. We need something of the form, say, HF plus of minus y with F coefficients to HF plus of minus y0, where it would be really nice if we had F coefficients, but it's not going to work. So maybe I'll just leave a question mark in there. It's going to turn out to be these Fn coefficients. And on this side, we want just, say, a -1 over n with, again, F coefficients. But it doesn't, like I said, it doesn't quite work with just f coefficients in the middle. So instead, we have this theorem of Hedden and Mark that there's an exact triangle of exactly this form, where in the middle, we instead have FCN coefficients. And on the two sides, we just have regular f coefficients. And that's the exact triangle we'll use. And finally, the last ingredient to our proof is just simply that if your fractional notice coefficient of your open book is less than 1, then this map G here sends this twisted contact class that lives in this FCN coefficient system associated to your capped off open book. It sends it to your original contact class. Sorry, this should be with endane twists. And this should be, okay, yeah. This should be, in that case, not less than 1, but this should be less than, say, minus n plus 1. There we go. But the point is essentially like, really the theorem as it's written kind of in my paper, or that you should think of it, is not that it's like confined to this particular case here, but that as a general theme, if you have some open book with fractional notice coefficient less than 1, then whatever map you're looking at in Hegardt-Floer homology associated to capping off, whether it's this map here or just say the cobordism map associated to capping off or whatever, it's going to be natural. The contact class is going to be natural under that map. Okay, so a similar statement also holds for cobordism maps and just HF plus of minus y with f coefficients and FCN coefficients as well. So you don't need to be looking at this kind of like mixed map from FCN coefficients to f coefficients. Just as it's natural under any of the maps is the point. So how does the proof go of this theorem? Well, if you look, there's kind of two canonical pictures that you can visualize here. This first one is with the fractional notice coefficient greater than 1, and the second one's with your fractional notice coefficient less than 1. And the idea is that you always have this natural triangle in both pictures, but you don't want to have any other triangles besides that one. If that's the only triangle that you have, then that's good, because it tells you that your generator X, which generates your contact class for your capped off open book, is going to go to your generator Y, which generates your contact class for your uncapped off open book. And on the right side here, you can see that there are no other triangles. But on the left side, you actually do have other triangles, like, for example, the one that we saw in the previous one, where in the previous example, where if you kind of go around the back here and then come around the front, then, for example, you map to this generator that's circled right there. And so for fractional notice coefficient greater than or equal to 1, there are other triangles. But for fractional notice coefficient less than 1, there just aren't any. There are no other triangles that you can count. And so since there's this unique triangle, you know that that contact class for your capped off open book is mapped exactly to the one for your uncapped off open book. Okay, so finally, let's just go through a proof of the main theorem, and then I'll call it there. I don't want to go too far over. So again, let's just remember what the main theorem says. So if you cap off some open book and get that the ambient manifold of that capped off guy is a rational homology sphere, and either your original open book has fractional notice coefficient less than the negative of the dimension over f of HF plus reduced of your original ambient manifold minus 1, or just the same thing where you are allowed to get rid of that minus 1 and instead add less than 0 on some other fraction or on some other boundary component, then you get out that your reduced contact invariant is 0. And this is the theorem that everything else follows from that I mentioned above. Okay, so how does the proof go? So we're actually going to fix here that n is going to be this dimension, dimension over f of hf plus reduced of minus yf plus 1. And now notice that for the sake of contradiction, if your reduced contact invariant of your capped off open book is non-zero in the reduced Floer homology, then two things happen. The first thing is that your twisted contact invariant of your capped off open book has to be non-zero. And the second thing that happens is that your intersection with u to the j has to be equal to 0. Some j. And that's just because of the characterization of the reduced Floer homology, with or as the co-kernel of u to the j. So that's telling you that there's some j where it's not in the image, essentially. So now from the rank theorem that I mentioned before, this tells you that the dimension over f of your twisted contact class is equal to n. And that's just simply because they're either all 0 or linearly independent. So since your contact class is non-zero, it has to be rank n. And now we look at the Hedenmark exact triangle, and we chase where everything goes. So your twisted contact class of your capped off open book is living here. And what we're going to look at is we're going to look at how it goes to this guy where we add n Dane twists along your first binding component in there. So now, if we have, say, for example, in either of the two cases, 1 or 2, where n is this dimension, if we have that our first Dane twist coefficient is less than minus n plus 1, then we surely have that the fractional Dane twist coefficient where we add n Dane twists along the boundary component should be less than 1. So by naturality, this tells you that under this map G here, your twisted contact class goes exactly to contact class of S with n Dane twists added. And now finally, the last thing that you need to argue is that since the dimension of your twisted contact class of your capped off open book is equal to n, and its intersection with u to the j is equal to 0, then it follows that your capped off twisted contact class inside of minus hf plus of minus y0 is not in the image of this first map f. And the point is essentially that the size of the co-kernel of f, or sorry, the co-kernel of u over here is by definition the dimension of the reduced Floer homology. And this map f is u equivariant, and so you can just make an argument that way that it can't possibly be the image of f. And so then this just tells you that this fractional Dane coefficient along any binding component where you add n Dane twist has to be greater than 0, and then it's just a similar argument to the one that we saw before, where it tells you that your original Dane twist coefficient has to be greater than minus n, which is a contradiction because we assumed that it was less than minus n. Okay, I'll stop there.
Okay, so questions for our speaker? Okay, so I have one question, Braeden. So from your theorem, one can see that after capping off many times you can detect that, okay, this is the resulting context structure is tight by looking
Mm-hmm.
at that the contact invariant doesn't vanish. So in some cases there have been works uh, regarding this, so for example, you gave some example, you gave the example of Baldwin et al., where they considered pseudo-Anosov maps and all that.
Yeah.
But there have also been examples where like pseudo-periodic maps or periodic maps,
Mm-hmm.
and they are similar by giving similar kind of bounds. Uh, uh, One result is there by Pablo or something. I am forgetting it, the name. So what he says is, looking at the power of by looking at the dent-twist coefficients, you can actually say that when your periodic map gives an open book, or just when your periodic map can be written as a product of positive density. So it kind of gives the extreme case of Stein filling. I mean, even
Mm-hmm.
stronger than Stein filling. It says that it can be written as product of positive density.
Mm-hmm.
But uh, but the proof he uses is completely different. Like it comes from resolution of complex singularities and all. But
Mm.
your proof is like to the other end, that it is more efficient in detecting tightness. So, but
Uh-huh.
do you have anything in mind that goes towards the hierarchy of tightness?
Mm. That's a good question. So maybe one way that you could start to see like fillability or non-fillability, etc., um, is that this theorem here is just telling you that your reduced contact invariant is 0 in this case.
Hmm.
And it turns out that if you have, say, an indefinite filling, then your reduced contact invariant has to be non-zero. So it's not just that your contact invariant is non-zero, but that your reduced version of it is non-zero if it's indefinite. And so you can see this theorem is telling you that if you have some sufficiently small Dane-Twist coefficient, then after capping off, you get some non-indefinitely fillable contact structure. Is maybe one thing that you could immediately say. Um, I've been thinking along those lines as well about trying to find, for example, like contact structures with no indefinite fillings, something like that. Other than that, though, I think, yeah, the hard thing is knowing that if your contact invariant is non-zero, then you are fillable or something like that,
Yeah,
which is not necessarily true.
true.
I guess for if you wanted to know about fractional Dane-Twist coefficients telling you something about being Stein fillable, etc., I don't know. Besides kind of the results that I've mentioned a couple times throughout the talk about, say, like if your fractional Dane-Twist coefficient is greater than 1, then how that theorem goes is that if it's greater than 1, then you have an indefinite filling, and then your reduced contact invariant is non-zero. Other than things like that, I'm not sure. But I think that's a big open question that I'd be interested in hearing about. Um, Definitely, but I'm not sure about how I would approach it at the moment.
Yes. Thanks.
Yeah.
Yeah. So, Arijit and Shomo, do you have any questions for Britain?
Oh no,
Yes, Arijit.
oh no, I don't have any.
Okay.
So I have to look.
Okay. So in that case, let us thank our speaker, Braden. Really nice talk. I appreciate that. Thanks.
Yeah, thank you. Yeah, thanks for the opportunity for speaking here. This was really fun giving two talks. Gives you a lot more room to say more
So
things.
can you suggest me any reference to study?
Oh,
Like
what's that? Sorry?
Braden.
Yes.
So,
Can
yeah.
you suggest me some references? So
Some
for
references.
beginners to study Head-Floor homology based with open books, yes,
Yeah,
references.
Haggard Fleur and open books. Yeah. I would start with probably the original Ojvath and Szabo paper. If you just search like Ojvath Szabo contact class or something like that, then that will be that will probably come up. Uh, it depends what you want to do with Haggard Fleur homology and open books. Another good one also is the Honda Kazez Modic paper where they show that the contact invariant is generated by this intersection point that I wrote down. It's like on the contact class in Haggard Fleur homology or something like that. Uh, Another good one that's kind of related here, which I kind of glossed over, but it's essentially the basis for this paper, is one by my advisor, actually, John Baldwin, which is about capping off and the contact class in Haggard Fleur homology. It's kind of like the precursor to these results here. That one's also pretty good too. There's lots of others that I'm not thinking of off the top of my head, but I could, yeah, if you wanted to talk more about it, I'd be happy to tell you more references to look at.
Okay.